I'd like to go ahead and get started if we could, and welcome you to the 6th session of Groundwater U. Yeah, we could say that. This Groundwater U, has anybody not been here yet? Everybody's been to one of these before? Okay, then we're just going to go real quick. This is the 6th session, Contaminant, Fate, and Transport at Santa Susana Field Laboratory. These are the Groundwater Advisory Panel members. They're all here tonight. We're getting things posted as quickly as we can. I'm not positive that session 5 video is up yet, but anyway, we're doing our best on getting things posted. It is. Well, good for us. Yay. So tonight, are you doing the introduction to the panel again? Okay. John Cherry is going to be the primary presenter, and then we'll finish up with questions and answers at the end of the evening. If you're not getting emails from us, and you would like to be getting emails from us, please give Jasmine your email address, because it either means we never had it or we don't have a good one for you. And we'll talk later about the possible session 7, and we'll need to have an ability to notify you about that. So, ground rules. I'm going to introduce a new ground rule tonight that I didn't have prior to tonight, but at the last session I felt I needed it. So, limit distractions, turn off your cell phones. Mine is almost dead, but I'll turn it off when I sit down. Hold the questions to the end to the extent possible, and remember to ask questions that are germane to tonight's topic. Use the microphone when you're asking questions so that the videotaping can capture you. And save your comments on the Groundwater Investigation Report until DTSC's public comment period. And then the last one that I've added, because I needed it last time, is that treat others with respect. And I know there's a lot of opinions in the room, and we appreciate that, but please, if you disagree with somebody, remember to treat them with respect when you disagree with them. So I used that ground rule, even though it wasn't on the list last time, but I wanted you to be aware that it's on the list this time. So with that, where did Mark go? Oh, Mark has a few things he'd like to say.
Good evening, and normally Tom Seckington has done the previous 5 of these. Unfortunately, Tom is at home with a sick daughter, and he very much regrets not being able to be here tonight, but I asked him to type up just a few words, his script, if you will. And on behalf of DTSC, we do want to thank you for coming to this 6th session of the Groundwater U. Tonight's lectures are specific to the contaminant, fate, and transport issues related to the Santa Susana Field Lab. And the advisory panel of Dr. Cherry, Dr. Parker, and Dr. McWhorter are very well-respected professionals, individuals within the hydrogeology environment. They have a lot of background in this. That said, they are part of the Boeing group, and they are being paid by Boeing and by NASA and DOE for their advice in this advisory panel. As Tom has said many times, the disclaimer that DTSC is putting on this is that there are things, this advisory panel is presenting their opinions, and it does not necessarily represent DTSC's opinions. They represent what is in the Groundwater Remedial Investigation Report that DTSC is currently reviewing. So we may agree with some of the things that they're saying, we may disagree with some of the things they're saying, and we may have no opinion on some of the things that you're going to hear. The Groundwater Remedial Investigation Report is currently available on the DTSC website, and it's broken right now currently into about 70 different pieces, all less than 25 megabytes, to aid those of you who may not have high-speed dial-up. It does take some time to get all 70 files downloaded. I had a request to see if we could actually put a single file up for that. I will be working on that next week to see if we can get just one file up to make it a little bit simpler for those of you who do have high speed. So, to that end, the DTSC website on the Santa Susana has a Santa Susana Field Lab web portion of it. And so we just direct you to take a look at, that you can go and review that document there. We will be noticing a public comment period. I'm hoping that we do that before the end of this month. We expect that public comment period to run sometime into August. But again, the document is currently available for you to provide us written comments. And so with that, I'm going to close it out and give it back over to Wendy. And again, thank you for coming tonight. Certainly appreciate it.
And I'm actually just going to hand it to John, but I'm also going to give him the clicker. So, oh, you've got that one. Okay. So,
good evening and welcome back. It's nice to see so many familiar faces. But I guess that's because you know there's no exam in this Groundwater U course. You've figured it out. You get your grade based on attendance, so we have a lot of high grade people in the audience this evening. I was going to introduce the panel, but you've all heard this before. Beth's from a dairy farm in upstate New York where they had a water well that served all their water needs. Dave's from a ranch up in the hills of Colorado, and they also had a water well. I'm from a small city north of Montana, and we didn't have a water well, but a shortage of water was a big deal in that part of Canada for over the decades, Saskatchewan. So I guess we got into this field because of water wells and shortage of water. I've noticed over the years there's a higher propensity for people to go on to study groundwater hydrology who have actually been from rural areas. And we arrived here from Colorado and Ontario in 1996, and we were invited by Rocketdyne, a member of Rocketdyne's environmental staff, who met us at a short course in San Francisco in 1994, where Beth and Dave were talking about things that were very relevant to this site. So they invited us down to take a look at the site to see if our expertise would have relevance. And we concluded it would, and we signed on to be a panel. Nobody told us about the 15 years of this panel, though, but it's been very interesting and enjoyable. And so the panel was set up with a mission, and we've distilled our mission down into these 4 questions. Where are the contaminants that entered the ground decades ago now located? Why are the contaminants located where they are now? Where are they heading, and how fast are they moving now and in the future? And then ultimately, to provide some perspective on what can be done to mitigate any adverse effects. And so, as was mentioned, this is the 6th Groundwater EU session. And I'll be speaking on that in a moment, but I'll ask Dave and then Beth to give a brief overview of their talks just as a background introduction. But before I get to that, just to remind you why we're all here. The panel's here to provide these sessions, to provide you with information to help you better understand these 2 big reports that we'll be mentioning more when we get on. So we hope that you'll look at these reports, and we'll talk about their nature as we go along, and that's why we're here. Dave, I'll turn it over to you.
are you Mike?
Just a quick summary. You all seen this before now, and some of you have seen it twice. So this will be the 3rd time. We looked at estimating the recharge on the site, and through a variety of methods, we've decided that the recharge on the site is, on the upside, about 200 gallons a minute. The recharge on the site creates a mound beneath the mountain that stands hundreds of feet above the surrounding valleys. And this implies that there has to be a substantial resistance to flow in the mountain in order for that mound to remain at those elevations. A portion of the recharge that enters the mountain discharges along the slopes of the mountain in springs and seeps and to phreatified areas, and a portion of it follows deeper flow paths and goes out into the surrounding valleys, Simi Valley, San Fernando Valley. This is a picture of some of the seep areas and the phreatophytes that are on the site. More than 100 of these have been identified, and you'll hear tonight that there's still work going on with respect to these seeps. Virtually all the groundwater at the site occurs in the matrix. About 13% of the entire rock volume under the mountain is pore space, interstitial pore space, or what we call matrix porosity, and that's where almost all the water is. The fractures themselves provide only a very small part of the pore space, and with respect to storage, the fractures themselves are negligible. On the other hand, the fractures are the main players with respect to how the groundwater moves and flows. And this is indicated by the fact that the hydraulic conductivity of the fractures is 50 or maybe even 100 times more than the matrix porosity according to all of our measurements. Yes, the fractures, I'm not sure which sentence. Well, the fractures contribute almost nothing to the storage of the groundwater, but they are the main players with respect to controlling the groundwater movement. And that's indicated by the hydraulic conductivity figures here, which show that the fracture hydraulic conductivity is 50 or maybe even 100 times greater than the matrix hydraulic conductivity. All right, Beth, I'll let you summarize your talk last time.
Okay. Good evening. So I talked about source zones, and in particular from a subsurface perspective, and I focused on the migration mechanisms for these contaminants. These transport processes that we talked about are advection, so the movement of fluids in the fluid phase, building off of what Dave talked about with groundwater flow, and then also talking about DNAPL, dense non-aqueous phase liquids, such as trichloroethylene or TCE, and the fact that it, as a solvent phase, is also essentially flowing as a fluid in these fracture networks that we have been talking about. The other process that I talked about was molecular diffusion, and that's occurring in the aqueous phase due to a concentration gradient in the water. And I also mentioned briefly sorption, and the rest of the reaction processes are going to be talked about by John Cherry later on this evening. So we showed some movies, and after a little bit of fiddling, they worked last time. My fingers are crossed again. But we talked about diffusion here, and this is a movie that shows how diffusion occurs, where we have high concentration of TCE at the base of this column of sandstone, and the sandstone has a porosity of 13%, as Dave mentioned, and it's completely filled with water, but the water isn't moving in this example. We have the possibility, though, of TCE dissolved in water at the base of this column to diffuse upward through this column of sandstone, and that's what we'll be looking at by watching this middle column here. Colors of red will show a range of TCE concentrations in water. And this is a movie essentially of diffusion in the Chatsworth Formation sandstone with a 13% porosity, a small amount of sorption over a 50-year period of time, and the distance scale is ranging from 0 to 250 centimeters, or essentially 2.5 meters, or 2.5 yards, and over 50 years, which is what we're starting to approach now, we can see that we have measurable concentrations almost 2 yards or 6 feet into this sandstone, only by diffusion transport. So it's an important mechanism for transport, and it's also a very important process at Santa Susana. Another key finding that we talked about 2 weeks ago was the importance of this diffusion process on the movement of the contaminants that are initially getting into the subsurface and moving in the fractures, just as Dave mentioned, where groundwater is primarily moving. But over time, that mass is being transferred into the matrix, the low permeability matrix blocks between the fractures, by this diffusion process. So we have an early time condition when TCE, represented here as a solvent phase or DNAPL phase, has moved through the fractures and distributed into the subsurface, as we see here. It dissolves into the water, and that concentration in the water in the fracture or into the matrix in contact with the fracture allows a concentration gradient to drive the mass into the matrix, and we see that dissolves some of the DNAPL volume, and over time we completely lose that solvent phase in the fractures and have a diffusion halo or a fingerprint essentially of that contaminant mass in the matrix where it used to be in the fractures. So we carried on last time and then looked at detailed investigation work at the site in terms of where the contaminants are located in the subsurface in the present day based on our detailed investigation work. So here we have a perspective diagram that shows what the nature of the contaminant distribution might be perhaps in a cartoon way. So we've got a test stand being one of the one of the types of source areas that we have at the site where TCE was used in the solvent phase and could have entered the ground in some retention ponds moving along the fractures, and then as the previous slide indicated, dissolving over time. But then we also have groundwater moving through that fracture network creating a plume. So what we're trying to study here in detail is the nature of the contaminant distribution along this entire slice, this vertical slice through the center of the contaminated volume. And the results from our detailed study in the northeast corner, which is shown here, our detailed study area is the part of the plume that's emanating from the property off-site. And if we look at a close-up of this study area, we had 5 cored holes along a source transect and 3 cored holes and a monitoring well along what we call the plume transect. And the data that I'm showing here in the bottom part of this slide is along our center line or long sect through the middle of the high concentration zone in the direction of groundwater flow. So if we go to the bottom slide here, we have a color scale that represents the range of concentrations over a factor of 100,000. So several orders of magnitude. And the important contour interval here is going to be the 5 microgram per liter contour, which is represented by this aqua and light blue shading. So on the left-hand side here, we've got depth or distance below ground surface, and on the x-axis we have distance in the direction of groundwater flow, and we have our highest concentrations on our left boundary emanating a distance of about 1,000 feet down gradient here as it transitions from red to orange to yellow, with a slight detect here, a distance of 3,000 or just over 3,000 feet down gradient. So most of our contamination has been found close to where it got into the ground, as evidenced by this detailed study area and the highest concentrations being real close to where they got into the subsurface decades ago. So our fourth key finding 2 weeks ago talked about the fact that these plume fronts, I guess I could point that we refer to this part of the plume here at the leading edge as a plume front. Those plume fronts are not moving rapidly forward after 4 or 5 decades of migration. And what we've delineated here, the nature of the contaminant distribution indicates that these plumes are less than a mile long, and the calculated distance the groundwater would have traveled in the same time period is greater than 25 miles. And that retardation effect on the plume front is due to this matrix diffusion and a bit of degradation, and John Cherry will talk about some of these reaction processes in more detail. And our final finding that I presented, and again we'll pick up on this again tonight, is that plumes have not reached off-site seeps or springs. Dave talked about that about half of the recharge on the site is discharging on the sides of the hill slopes, and the other half is going deeper down below the valleys. And at this particular slide is emphasizing where the contaminants are arriving, and that we've essentially detected TCE at 3 seeps that are on the property, and they would represent the shorter flow paths from some on-site contaminated areas as indicated here. But the off-site seeps have been non-detect. And this is where I'll turn it over to John to carry on with the contaminant story.
Thanks, Beth. So my title here is Contaminant, Fate, and Transport. Sometimes we write it Contaminant, Transport, and Fate, and that's our special jargon in our field. So when people say, well, what do you do? You know, what's your profession? What are you doing? We say, oh, well, we study fate and transport, or transport and fate. And so somebody may ask you this evening after the lecture, what did you do this evening? And you attended a lecture on transport and fate. And so we need to settle on what we mean by this so you can say what this lecture was about. And in fact, Beth's lecture was all about transport and fate, so I'm just continuing on the story. So transport then refers to the carrying of the contaminants under the influence of groundwater flow, which is advection and diffusion. And then fate refers to other things that operate on the contaminants, for example, sorption, to transfer the contaminants from the water to the solids, and a change in the chemical species that I'll talk a lot about in a few minutes. Or in fact, the fate of a groundwater contaminant might be that it's discharged to the surface. So the fate of a plume might be to discharge to a river, a stream, or a wetland. Okay, so that's transport and fate. This session is divided into 8 modules, and we'll have a little stretch break, I think, after module 4. And we'll just work our way through these modules, and at the end of each module, there'll be a little summary so we can recap as to what happened. And the first module is about the scientific method, and you would wonder why that has to be here. Why don't we just get on with it? But I think it's important to have a little discussion of this. So here are these big documents that we're having these sessions for, so you're better able to look at them. And they're thick, lots of pages, etc. And there's the RI, which is the remedial investigation, the groundwater remedial investigation. And then there's the SCM, the Site Conceptual Model document, and I'll mention more as to what that means here in a moment. And these documents are very interconnected, so basically to appreciate and understand the RI, you need to read a major part of the Site Conceptual Model document. And when we say that both of these documents are based on a scientific method, we mean it's based on a particular methodology that we scientists are supposed to follow in order to arrive at our conclusions. And the purpose of the scientific method is to minimize or eradicate personal bias. So we all have a personal bias, and the scientific method is intended to try and minimize that or eradicate it. So at the end of the day, it isn't the opinion of the scientist that matters. At the end of the day, it's whether or not the methodology has been followed and whether or not the data supports the conclusions in the documents. So basically, in the scientific method, you ask a question that you're seeking an answer for. You do some background research so you know more about the nature of your question, and then you construct a hypothesis, and then you acquire some data, some more data, and then you analyze the results, and then you determine whether your question was answered or your hypothesis has been confirmed. And if it's been strongly confirmed, then you would probably quit gathering data and write your report and leave. If your hypothesis hasn't been strongly confirmed and you need an answer to it in more detail, then you do another round of your investigation. And so we go round and around in this process, and you can see there's a red box there that says fill data gaps. And as we speak, data gaps are still being filled, and we'll mention some of those as we go along. And throughout all of this process, if we're following the scientific method, we have to maintain an open mind and be open to the possibility that there are other explanations, multiple working hypotheses, so there are other explanations, and we're supposed to have continual skepticism. And you, the audience, of course, need to have continual skepticism, and as you read these reports, you need to be skeptical. Look at the information and wade your way through it and ask questions, etc. So the RI report, the Remedial Investigation Report, is structured in a certain way that's done in the regulatory mode, and it contains all of the information. So it's got tables and graphs and appendices, And all of the information is there on a bunch of big charts and whatnot. So it's basically where all the information resides, and that leads then to the concluding statements or the concluding hypotheses. The Site Conceptual Model Report is arranged in a very different way. It doesn't have all of the supporting data. It has pieces of the data that we pull out in order to address particular questions. The Site Conceptual Model Report is divided into a number of sub-reports that I'll mention more about here in a moment. Site Conceptual Model, what is that? And this is a definition pulled off of the web, which is good as any. Basically, the Site Conceptual Model organizes the information in a clear and transparent structure that facilitates identification of data gaps. And a Site Conceptual Model is one of the primary planning tools used for decision making. And Site Conceptual Model has become a very important word in our profession. It's such an important deal that US EPA in 1993 embedded all sorts of instructions as to what you need to do if you're going to build a site conceptual model for a contaminated groundwater site. And this is just one of the pages from that EPA document. And it lists all the many hundreds of types of things you're supposed to think about and look at and have incorporated as your information base when you build your site conceptual model. And certainly that's what we've done at the Santa Susana site. The Cal DTSC, of course, speaks about the need for site conceptual models, so that's part of their framework. So when it comes to studying contaminated sites within the regulatory framework, you need to build site conceptual models, and that's basically the application of the scientific method. So the site conceptual model document is divided into 64 individual articles, each one in length from somewhere between, say, 5 and 50 pages. So if you choose to read it, it's like reading a book of short stories, where each short story kind of is meant to stand alone. And each of the short stories addresses a particular part of the data, where we say, let's take tritium, for example. Tritium indicates so-and-so, and then we put all the tritium data in there, and we do some calculations, and then we lead to a conclusion about tritium. So in order to arrive at a conclusion as to whether our ultimate summary, our ultimate conclusions on our site conceptual model are founded on science, you have to look at each one of these 64 documents and judge it on its own scientific merits. Now, each of these 64 documents are prepared in what we regard as a peer-reviewable mode. Okay, they're prepared as an article that we either have submitted to a referee journal or we will submit to a referee journal. And if that's not the case, it's prepared to be peer-reviewable in this particular way. And what does that mean? For an article to be accepted in the scientific community, we do all of our work and we write our article and we send it to the editor of the journal. The editor of the journal receives the article and then sends it out to 3 peers. And the peers have to be experts in the area of the article. Okay. And to be an expert in the area of the article, that means they have to publish and have proven that they've done previous research in the area of the article. And so these 3 anonymous reviewers, because you don't know who they are if you've submitted the article, then they scribble all over your manuscript and tell you how weak your ideas are or whatever. And in some cases, they say the article isn't fit to publish because you're confused and you don't know what you're doing. In a good number of cases, they'll indicate, yeah, this is worthy of publishing if the authors will make a whole bunch of corrections. So it's a very tedious process that we go through, but that's what peer-reviewable science is all about. And then it's published, and it comes out in the literature on the web all over the world, and that means that a scientist anywhere can read the article and say, aha, these guys have made a mistake. I'm going to write the editor and point out what the mistakes are. And if the mistakes are valid, then the mistakes get published in the journal, and then you read in the journal of what a dummy you've been because you've done your equations wrong or whatever. And every once in a while we make mistakes and we see in the literature, oh my land, I got that equation wrong and whatnot and so forth. And all you can hope for is that the mistake isn't too serious. So that's the peer review process that's been put into the SCM, and that's why it's divided into 64 articles and why we're still working away to get these articles in shape and send more of them off to journals. Now, in addition, in the EPA regulatory framework, there's something called the DQO process. And that is a process whereby every time you're going to mount a phase of your study, you have to specify very formally a number of questions you're going to answer. And then you proceed to answer them. And you look at the data from that next phase, and then if there are still questions that remain to be answered, you do another phase, et cetera. So it's a very formal process to avoid inefficiencies and basically just going out and getting data and having fun without any consequences at the end of the line.